Okay, so in 8.4, we are going to begin down a process, which we'll do for the next few sections, of looking more closely at infinite series and trying to determine whether they converge or diverge. So here's our big concept. Does a series converge or diverge? So what we're going to do is we're going to develop a series of tests that we use when we're looking at an infinite series to try to figure out whether it converges to a value or whether it diverges. And again, diverges means that when you're adding up the terms of the series, that the result that you get does not settle in on a value. It may be that it heads off toward an infinity, or it may be that it just doesn't settle on a value because it's alternating or something like that. But to converge to a value means that the limit of the partial sums is approaching some set number. So let's remind ourselves this idea. So S equals the limit as n tends to infinity of S sub n, and that this is the limit of the partial sums. So we will have tests for trying to figure out whether a particular one converges or diverges. But again, you can think about it yourself just to get a sense of what's going on. You can also explore some of these problems numerically by perhaps evaluating a partial sum down the line and see if they seem to be settling in, et cetera, et cetera. So let's look at an example. So if I have the summation as I goes from 1 to infinity, so this means that this is an infinite series. And let's say my terms are 9 times 10 to the minus n. Okay, so what I'm showing you here is a series in which we are adding it up. It's infinite, and the formula is given explicitly for what the terms are. So to try to help understand what this is, we could write out the first few terms. So and the way you do that is you let I be a 1, a 2, a 3. Oh, I said I, and then up here I put an n. Let me fix that. My letters aren't matching, so I'm going to take away that n and make that an I. It's a dummy variable, but they should match. Okay. So for example, if I is a 1, then this is 9 times 10 to the minus 1, or 9/10. And then I add to that what I get when I is a 2, which would be 9 times 10 to the minus 2, or 9/100. And then I would get plus 9/1000. And this would just keep going on forever. So this is an example of an infinite series. And if I write out the first terms, it's a little easier to see what's going on. And then to make it even easier, I'm going to use this in decimal form. So I'm going to write an or here because these are equivalent. I didn't actually improve anything, but some people do like it written better this way. And so as we've discussed previously, this infinite series ends up becoming 0.9 with a bar that repeats, and we've made some discussions about why we conclude that this is a 1. All right, so why are we looking at this? I just want to have people be able to have in their mind the idea of what we're looking at. And then we can start to look at more and more complicated examples. So while we're looking at this example, let me point out a couple things about it. This is an infinite series, but it's a particular kind. It's the type we talked about last time. This is called the geometric series. And the way we can recognize this is a geometric series is because the way we get to the next term in the sequence of terms that are being added is the same way every time, by multiplying by a constant. And so let's remind ourselves that we had a formula. This is a geometric sequence, or a series, I should say. And there is a formula for the result of a geometric series in which you take the first term and you divide it by 1 minus the r value. And so again, this was built on the, sorry, I forgot to turn off the volume of my phone. Let me try to do that now. My children's schools keep calling with more messages. There we go. So this is true when the absolute value of r of your geometric series is less than 1. And you have this formula as a result. So let's say when. And so we can test our formula in this case. We were already able to evaluate this just from previous work. Volume 2, there we go. We were already able to evaluate this from previous work, but in this case, I could note that the first term of my series was 9/10, and that the r value that we were multiplying by each time was 1/10. And so in this case, s would be equal to 9/10 over 1 minus 1/10, which is 9/10 over 9/10, which is 1, which we already knew because we know 0.9 with a repeating decimal is 1. But nonetheless, so here we have an example of an infinite series that converges. And because this particular infinite series was a geometric series, we could even use this formula just using the first term and the constant successive ratio of what you're multiplying by each time to produce what the sum of that series would be. Okay, so these are examples. So now let's consider another example. So the next example is we're going to have the summation as I goes from 1 to infinity of 1 over I. So there's a name for this, but let me go out the first few terms first. So when I is a 1, we get a 1. When I is a 2, we get a half. When I is a 3, we get a third, etc. This series is very important, and so it gets its own name. This is called the harmonic series. So, like with any series, the first thing we could try to consider is, does this series converge or does it diverge? So we can imagine the partial sums. I have 1, then I have 1.5. Then if I add a third to that, I'm going to think of that as like 2/6. Then I get 1 5/6. So that's a little less than 2. Then I add 1/4, etc. Is there a question there? Okay. All right. So the question is, does this converge or diverge? Does the harmonic series, since this one gets a name, does this converge or diverge? And in particular, I'm using this as a good point because this is what the question will be for half of this chapter. Does this series that I'm looking at converge or diverge? And as I said, we're about to develop a bunch of tests to try to figure this out in general. But in the beginning, we can just try to kind of figure it out without the tests. Like example, the geometric series, which we just did, which we could see converged and even determine the value of a 1. And now we'll look at the harmonic series. All right, so to help, I'm going to make an analytical argument here because we don't have any other tools we can really use yet. Let's make this argument. So here's what the series looks like. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 1/7 plus 1/8, etc. Okay, so what I'm going to do now is I'm going to consider regrouping this addition in ways where we can simplify it a little bit to explore the idea as to whether these numbers settle in on an answer or not. As we've discussed in past, for example, with area problems, with improper integrals, where the function, we're taking the area under the curve as it goes off to infinity, that basically if you're adding smaller and smaller numbers onto a total, it's possible that you settle in on a value. And we are doing that. We can see here we are adding smaller and smaller numbers, but the question is, does that settle into a value or not? So here's a way to think about it. So I'm going to look at these two terms added together, a 1/3 and a 1/4. And what I'll point out to you guys is that as the terms are going down the line, they're getting smaller. So 1/3 is a larger number than 1/4. So imagine that I consider that this sum then is less than, let's try that again. Is less than 1/4 plus 1/4. And 1/4 plus 1/4 is 1/2. So I have, I'm sorry, I said less, I meant to say more. I'll figure this out. More than 1/4. So that means that these two numbers added together are more than 1/2. Now I'm going to consider the next 4 numbers all together. And the sum of these 4 numbers is more than if they were all the smallest of the 4, which is 1/8. So the next 4 numbers are more than 4/8. So I've set up a pattern here to try to explore whether this infinite series converges or diverges. And the pattern I have here is that the first number is a 1, and then we have a 1/2 added. Then the next 2 numbers will total more than 1/2. Then the next 4 numbers will total more than 1/2. Then I could go for the next 8 numbers, which would end with 1/16. And they would total more than 8/16, since each of the numbers there is at least as big as the last one. So the next batch over there would be more than 8 times 1/16, which is also 1/2. So what we're seeing here is that the sum of this series is more than 1 plus 1/2 plus 1/2 plus 1/2, etc. because I can always go out enough terms. I have to go out 2 terms in the beginning, then I have to collect 4 terms to get more than a half, then I have to collect 8 terms to collect more than a half, but I can do that indefinitely. I can do that as many times as I want. So basically the series is more than an infinite number of 1/2s added together. Therefore, the limit of the harmonic series is infinity, and it diverges. Questions, comments, discussions about that? Okay, so I wanted to begin by just an example of a series that converges. So we looked at this, this initial geometric series that converges to 1. And then also with the harmonic series as an example, because this is an example of a series that diverges in spite of the fact that the numbers themselves that are being added are getting smaller and smaller and smaller and heading towards 0, but it still diverges. So in this case, it will regularly be possible that we're looking at a series where the terms themselves are shrinking away to nothing, but we still don't know if the series converges to a value or diverges, or heads off to infinity, or doesn't settle in on a value. Questions, comments, discussions about this?
Oh, you're doing this in the bed.
Okay.
Maybe I thought you were in a wig still.
So somebody needs to mute their mic or ask a question.
I finished my math. Now I'm doing reading.
Okay. Sorry, Nikhil, I muted your mic for you. Okay, so I'm going to go ahead and give us a new page to begin to consider ways that we can test for this sort of thing. Okay, so let's begin to look at some tests and try to think and talk about how they might help us determine whether a particular series converges or diverges. The first one we're going to look at is Theorem 8.3, which is, I'm sorry, 8.8. We're past 8.3. 8.8, which is on page 627. So this is the divergence test. So what does the divergence test says? It says if you have an infinite series, and they're just writing this using the summation of a sub k for a shorthand notation. If this converges, so any convergent infinite series, then the limit as k goes to infinity of the terms is 0. So what this basically says is that the only way it's possible for a series to converge, only possible, doesn't mean it has to happen, is if the terms go to 0. So an example, consider a summation. This time I'll use a n, as n goes from 1 to infinity of, let's keep it simple, 0.3. So this is what we call a constant series because the terms of the series are constant. And so what does this look like? This is 0.3 plus 0.3 plus 0.3, etc. Just keeps going on and on and on. We just keep adding the same number again and again and again. So this is an example where we are adding a small number, 3/10. It's not a very big number. But what you can observe from this is that the limit of the term itself is just 0.3 because it's a constant. It never changes. So as n heads off to infinity, you have the same term every time that's being added. Therefore, the limit is not going to 0. And so since we know from Theorem 8.8 that if the series converges, then the terms go to 0, that also then implies that if the terms do not go to 0, the series cannot converge. So I could for basically say that since the limit as n tends to infinity of 0.3 is 0.3, which is not equal to 0, then by Theorem 8.8, the series diverges. So what this means is that what the Theorem 8.8 does is it gives us a test to determine if a series diverges. If you pass the test, the series diverges. And the test is, does the limit of the terms go to 0? And if the limit of the terms does not go to 0, we can safely conclude, as in this case, that the series diverges. Now, if the limit of the terms does go to 0, then this test does not help us. And that's why our first two examples are good to look back at, because they show us that. So for example, our first two examples, both of them, the terms went to 0. The limit of the terms was 0, but one converged and the other diverged. So if the limit of the terms is 0, this test tells us nothing. But if the limit of the terms is not 0, then this test tells us the series must diverge. And this is an example where the terms themselves do not go to 0, therefore it must diverge. And that hopefully can make sense, because if I just keep adding 0.3 again and again and again and again forever and ever and ever, the number of the sum is just going to keep rising and rising, and it's going to go beyond any value and head off toward infinity eventually. Questions, comments, discussions about that? Okay, so maybe let's look at some of their example. So they give example 1 on page 628. And they give us 4 parts, but we'll just look at one of them. It says, using the divergence test, determine whether the following series diverge, or state that the divergence test is inconclusive. So those are our choices. The test either tells you that it has to diverge or tells you that it doesn't know. So let's consider number A, which is the summation as k goes from 1 to infinity of k over k plus 1. And we've actually looked at this before. So just to remind ourselves what this looks like, when I plug in a 1 for k, I get 1/2. When I plug in a 2 for k, I get 2/3. When I plug in a 3 for k, I get 3/4, etc. So this is an infinite series. So the question will always be, converge or diverge? And one of the things we can try to do to head toward figuring this out is consider whether the divergence test would tell us that it diverges. And this will be the sort of the immediate test to always keep in mind, because if this test applies, then that's going to be the easiest way to draw your conclusion, almost always. And so again, you basically ask yourself, well, just for this to have a chance to converge, the terms themselves cannot go to zero. Have to be going to zero, or just or won't have a chance of converging. So if the terms do not go to zero, it must diverge. If they do, then I still have to figure out whether it diverges or not. Then the divergence test would be inconclusive. So in this case, we could take the limit as k goes to infinity of what the terms are themselves, which is k over k plus 1. And we've done this limit before, and the limit of this is 1, which is not 0. Thus, we can conclude that the series diverges by the divergence test, which is theorem 8.8. And that's it. So if you can take the limit of the formula for what the terms are in the series, and it does not go to 0, then you can immediately conclude that the series does not converge to a value, but instead diverges. Questions, comments, discussions about theorem 8.8, the divergence test? And again, if you don't have a mic, you can type into the chat window if you want to ask a question there. I'm going to try to keep an eye on that. But if you have a mic and you want to just ask a question, you can unmute it and ask your question. Anything so far? Okay, so before we move on to the next test, let me point out that after they gave this test, they introduced the harmonic series, which I used as our second example, and they concluded that it diverges as I did with a sort of similar logic. They did a numerical approach and things like that. But let me just point out that the harmonic series, because this is a very important series, is introduced on page 628. And they actually spend more than a page discussing it, just to sort of go through partial sums, and they look at it graphically and numerically and stuff like that. So then after that page of discussion, they have theorem 8.9 on the next page, 629, which basically is a conclusion that the harmonic series diverges. So I tried to have us reach that conclusion with my little argument about how you could keep getting terms that add up to more than a half. And they sort of explore that and quite a bit more with, as I mentioned, numerical and graphical explorations into the harmonic series as well. But this ends up being a very crucial conclusion. Okay, so I'm gonna give us some fresh space here. I always forget to do after it goes up. Okay, so now let's look at the next one. So this is another test we're going to have to help us determine whether a series converges or diverges. And this is called the integral test. All right, so for the integral test, well, let's take a look at what it says, and then we'll look at an example to try to understand it a little bit. It says, suppose f is a continuous positive decreasing, lots of vocabulary, function. And for x value is greater than or equal to 1, this is true. And let the terms of a sequence a sub k be equal to f of k for k a member of the natural numbers. I know you don't like these symbols, but this is natural numbers. Let's put that in here. Natural numbers. Natural numbers, again, are 1, 2, 3, 4, 5, 6. They're just like counting numbers. All right. So what this means is we have some function and we have a sequence where the terms of the sequence are the same thing that the function would give you if you plugged those nice natural numbers into the function. So then, if that's the case, then if we consider the infinite sequence, the infinite series for the sequence, and then we also consider the improper integral from 1 to infinity of the function, then the series and the improper integral, they either both converge or both diverge. So let's look at some examples to try to understand what this says. So we are regularly working with the terms of a series and then treating those terms like they're a normal continuous function, like taking the limit as k goes to infinity or something like that. So we're often thinking of them the same way. And as I've been discussing previously, figuring out whether a series that's infinite converges or not is very similar to the work we did with an improper integral, where we looked at trying to figure if that infinitely long area tail could end up having a finite amount of area underneath it. So if we look at the harmonic series, so we've already have a theorem and we've already concluded that this diverges. But if you have a sub k equal to 1 over k, if you have the harmonic series a sub k equals 1 over k, and f of x equal to 1 over x, so then this is an example where we have an infinite series where the terms in the series would be what you would get if you plugged in nice natural numbers into the function 1 over x. So that a sub k is equal to f of k. Because they're just basically the same formula. Instead of a k, you have an x. So then note, the summation as k goes from 1 to infinity of 1 over k, and the integral from, not 0, the integral from 1 to infinity of 1 over x dx both diverge. And so if we had not gone through the work we did with the harmonic series to see that it diverges, and we had this theorem instead, we could have used this theorem to conclude directly that the harmonic series diverges, because we've already done this integral. We did this integral back in chapter 8, this improper integral, and we found that this was this special function which is divergent when you take the area under the tail off to infinity. So then consider the series k equals 1 to infinity of 1 over k squared. We could be saying, does this converge or diverge? This will be the question that we're typically asking ourselves for a series. So a sub k equals 1 over k squared. So if we let f of x equal 1 over x squared, then a sub k is equal to f of k for every value of k in the natural numbers. And because we've done this work before as well, the integral from 1 to infinity of 1 over x squared dx converges. I believe we figured out the value of this before was just a 1. So let's say I put that in here actually. Converges to 1. So since the improper integral of the function that expresses what the terms of the series are is an improper integral that we can evaluate, and we know that it converges, in this case to 1. Therefore, by this theorem, the integral test, so I'm going to put that, by the integral test, the series of the a sub k converges as well. So this test allows us to conclude that the series of 1 over k squared converges. So note, this does not tell us that the sequence, or that this series of a sub k's converges to the value of 1. It only tells us that it converges. To something. So even though the improper integral, because we were able to evaluate it, we know converges to 1, that fact by the integral test tells us that the series converges, but not necessarily to 1. It converges. In fact, in this case, it does not converge to 1. It converges to something else. Questions, comments, discussions about that? So they put that little caveat in the theorem as well. It says either they both converge or they both diverge, the series and the corresponding improper integral. But it states specifically in the theorem, in the case of convergence, the value of the integral is not equal to the value of the series. So this is our first glimpse into what I was mentioning before, that we are going to have quite a few problems where we are trying to determine whether an infinite series converges or diverges. And if it does converge, we're not even going to bother to try to figure out to what value it converges. We're just going to be stopped with being satisfied with the idea that it converges. Okay, so let's maybe try to do another example of the integral test. So they do this. This is example, one of the ones, example 2 in the book, which is on page 631. Okay, so we have summation as k goes from 1 to infinity of k over k squared plus 1. So the goal of the problem is to determine whether the following series converges or not. So what do we want to do? Converge or diverge? This is the question that we will be now doing for a few sections. Okay, so let's say we are just looking at this as a series to try to figure out if it converges or diverges. This is the big picture idea first, so that we can understand how we can begin to think and apply the tools that we're learning to the problems. So maybe the first thing is to imagine the divergence test. In other words, would the divergence test tell us quickly that this diverges? So that was theorem 8.8. So the divergence test tells us that if the limit of the terms themselves is not 0, it diverges. Otherwise, we don't know. So to consider the divergence test, I would be imagining taking the limit as k goes to infinity of the formula for the terms themselves. And so is this a limit we could figure out? What do you guys think? Anybody willing to chime in here? The limit as k goes to infinity of k over k squared plus 1.
Zero.
Yeah.
So we think that goes to 0. And how could we have figured that out, just to remind people and put their heads in the game? Is there some way we could sum up why we think this would go to 0?
You can use L'Hopital's.
Absolutely. You could use L'Hopital's rule because you have something of the form infinity over infinity. We've had discussions before about the end behavior of rational functions, because you have a polynomial on the top and the bottom, and the degree on the bottom is larger than the degree on the top. Then as they're going to infinity, the largest degree dominates. So it's going to go to infinity much faster on the bottom, meaning the bottom will become very large compared to the top. You can also use this to think about our rates of increase that we talked about before, because higher powers increase to infinity at a higher rate. You could also algebraically multiply the top and the bottom by the reciprocal of the biggest power. If you divide the top and the bottom by k squared, you'll basically get something going to 0 more obviously. In any event, so because the terms go to 0, what can we conclude about the divergence test? Basically that it doesn't help. So I'm going to write here, thus the divergence test fails, because it passes the test if the limit is not 0, because then we can draw the conclusion that it diverges. Fails to help. Now, of course, we know for this one, we're going to use the integral test because it's an example of the integral test usage. But nonetheless, in general, when you begin to now consider your position of just trying to evaluate series and whether they converge or diverge, the first go-to thing is to just double check in your mind. All right, let me just check first. Do the terms go to 0? If not, well, then I immediately know it diverges. All right, in this case, they do go to 0. So the next, we're going to say, can I determine if the integral from 1 to infinity of x over x squared plus 1 dx converges or diverges. Because this is the integral test. The integral test tells us that the integral of the function that has the same sort of formula as the formula for the terms of the series, if that improper integral from 1 to infinity can be determined to converge or diverge, then we know the same thing is true about the series. Now, it may be that we can't do that integral. Again, integrals can often be challenging to do. But if we believe we could do that and draw the conclusion, then the integral test would allow us to apply that same result to the limit. It wouldn't be, if it converges, the value wouldn't be the same, but simply they converge or diverge together. If one diverges, the other does, and vice versa. So then how would we look at this? That means to do the improper integral, we're going to take the limit as b goes to infinity of the integral from 1 to b of x over x squared plus 1 dx. So what do you guys think? Is this an integral that we can do? Don't like my x. All right, well, I'll help us along here. So we would do this by substitution, and maybe you can recognize that because the numerator of the fraction is just off by a multiple of the derivative of the denominator. So what I would do is I would do a u substitution, and I would let u equal the bottom. Chapter 7, coming back to haunt us. So then du is equal to 2x dx, and dx is therefore equal to du divided by 2x. Then I would do a substitution. So then I would have the limit as b tends to infinity of an integral. And so then I have x over u times du over 2x. And then if I want to go ahead and change limits of integration, I can do that too. So when x is equal to 1, then u would be equal to 2. And when x is equal to b, then u would be equal to b squared plus 1. And of course, I'm running out of space here. Okay, so can I go down? No. Okay, so let's go off to the side here. So this would be equal to the limit as b tends to infinity of 1/2, because I'm pulling this 2 outside. Just take note that my x's cancel. And then if I take I'm left with the integral of 1 over u du, so that would be the natural log of u evaluated from 2 to b squared plus 1. So I'm kind of running out of space here, so I'm just going to point out that this goes to infinity. Because as we saw before, I have a natural log of an argument where the argument is just being bigger and bigger and bigger, because as b goes to infinity, b squared plus 1 is going to infinity, and the natural log of something becoming infinite also becomes infinite. So therefore, the integral test says that the series of k over k squared plus 1, k going from 1 to infinity, diverges. Questions, comments, discussions about this example of the integral test? Again, they do this example for you in the book, as well as I think 2 or 3 others. Okay, so let's refresh the page after I go to the top this time. Questions?
Professor, I have a quick question.
Yes, ma'am.
So in terms of that problem we just did, like did we conclude that it diverges because the limit went to infinity?
Yes, so divergent means does not settle in on a specific value, a number. And so it can diverge by either going off toward infinity, or it can diverge by refusing to settle on a value, like completely oscillating back and forth between numbers or something like that.
Okay, thank you.
So yeah, we're not going to allow infinity as a result to a limit to be something where we say it converges. We're going to say that that diverges specifically. Is that satisfying?
Yes, that's good. Thank you.
Okay, so so now this means that we have 2 tests. We have the divergence test and we have the integral test. So I'm just sort of keeping note as we accumulate tests. So the next one we're going to consider is Theorem 811 on page 632, which is called the P-series test. This will be our third test to add to our list of possibilities. And so it states what it refers to as the P-series, which we've actually looked at before, so hopefully this will look familiar, which is a series as k goes from 1 to infinity of 1 over x to the power p in the bottom of a fraction. And it converges for p-values greater than 1 and diverges for p-values less than or equal to 1. So before, when I was talking about the improper integral of 1 over x, and we looked at this, and I talked sort of about as soon as the power on the x on the bottom of the fraction goes above a 1, then all of a sudden those integrals start to converge when you go off to infinity. As soon as the p, like an example that we've already seen is 1 over x squared, which we just did as an example for the integral test. So this is basically formalizing that big conclusion that 1 over x, or the harmonic series, is the exact borderline for that format to determine whether it converges or diverges. It's the borderline of divergence. So what we can see here is that the harmonic series is an example for this P-series test where P was equal to 1, And then if we have less than 1, it diverges. And if we have greater than 1, it converges. And the dividing line where p is equal to 1 is the harmonic series. So let's look at an example. This is example 3 on page 633. And again, there's several parts. Maybe we'll take a look at B. So it says, determine whether the following series converges or diverges. And we have the series. One over 4th root of k to the 3rd power. Does this converge or diverge? Okay, so again, let's think of the big picture here so that I can begin to try to sculpt in your mind the thought process that you want to go through when you are looking at problems in general. And so let me even be more aggressive with this suggestion. So you want to imagine as you're looking at series that you're accumulating a sense of this, that you're trying to develop some intuition about whether the series converges or diverges, because we're going to start to see more and more examples of series that converge or diverge based on one test or another. And so this gives us a sense of, well, when it looks like that, it tends to converge. And when it looks like something like this, it tends to diverge, with the harmonic series being the borderline between the two. So in this case, we have a power on k under a root, but a root can also be considered a power. And so we would basically want to try to recognize that and rewrite this with the power all up on the k, so we can basically use the p-test to compare it to. Oh, I spotted a mistake in my writing of the p-series up above, so let me fix that. So I wouldn't say, so I'm looking at this thing here. So my mistake is that I have a series in k, but then I wrote the default x variable instead of k. So let me just fix that, and if you have that in your notes, fix that. That's, of course, supposed to be k because this is as k goes from 1 to infinity, not x. Whoops. But I was just, you write x so many times in your life, you forget there's anything else that can be used. Okay, so that's a fixing of that. So that's k. All right, so now in this case, we want to say that we have a p-series. Again, a p-series is short for a power series because you basically have k to a power. And in this case, we have the series 1 over k. And when you have a rational exponent, the denominator is the power of the root and the numerator is the power. So this 4th root of k to the 3rd would translate into an exponent of 3/4. So we have p series like this with p equal to 3/4, which is less than 1. And so if we have a power less than 1, what do we conclude about the series?
Diverges.
It diverges, right? And it diverges because the p-value is less than or equal to 1. So we sort of basically can say, therefore, these 3 little dots mean therefore, the series diverges by the p-series test. Questions, comments, discussions about that? Okay, so I'm now going to blatantly skip over a little piece of what's done here. The idea, they spend about a page talking about how to estimate the value of an infinite series by having Theorem 812, which sort of focuses on how you could say what the remainder is after a certain point. But truth be told, this is something that goes back more normally to when we didn't have numerical tools to make it so easy for us to estimate. So nowadays, it would be much simpler once you had concluded that a series converged. If you then wanted to estimate what value it converged to, you could put the series in a calculator or online or whatever, and just put in a big number for k. And since you know it converges, with some big numbers for k, you could get a numerical estimate very, very quickly and easily. And we have a lot more stuff to cover. So I'm basically going to suggest that you try looking through Theorem 812 on your own as that shows up in problems, but that I'm going to move forward at this point, just to let you know. Okay, so let's keep doing this. Let's see if I can do this. Almost. So I'm just trying to keep these things up top. I probably should have just rewritten them, but still learning how to play with this format. Not too bad. Okay, so we now have these three tests, so that's why I'm leaving them there. We now have the divergence test, the integral test, so if series converge, not if they diverge, but if they converge to a number, that means that we have a limit of partial sums that exists. So that means that we can follow some of the properties of limits. And so we have three of them given to us sort of here. So for example, let's say that series of a sub k converges to some number a. Then the series where you have a constant multiple times the terms of the other series will converge to the constant times a. Basically meaning that when you're trying to deal with a convergent series, you can pull a constant outside. And we know that directly from some of the properties of series that we dealt with before. So this is basically the series of a constant times the terms has a limit that's the same as the constant times the limit of the series. You can pull the constant out. Similarly, if I have a series of a sum, that's the sum of the series. So then if the series of the A's converges to A and the series of the B's converges to some number B, then the series of the A's plus the B's converges to A plus B. And of course, this would also be true if this was subtraction. So again, what do these properties allow us to do as they have in the past? They give us a way to manipulate when we're working with terms of a series by pulling out constants and distributing the series calculation to individual terms inside, etc. And the last one is a little bit more interesting. So let's take a look at this. So it says if m is a positive integer, then the series as k goes from 1 to infinity of a sub k, and the series as k goes from m to infinity, so any positive integer m, so it could be 2, 3, 4, 5, up through a million of the a sub k's, either both converge or diverge. So the idea being that whether a series converges or diverges depends on what's going on as you head off toward infinity, not what's going on in the beginning. And you could sort of even prove this very, very quickly, because you can simply say that if you start at a later number in the series, like if I start after 1,000, well, the difference between what happens after 1,000 and if I go from 1 to infinity is just what happened in the first 1,000 terms. And that's a finite number. And if I add a finite number to any divergent series, that's not going to make it converge. Similarly, if I add a finite number to any convergent series that settles in on a number L, that's not going to all of a sudden make it diverge. Adding a finite number to convergent will not convert it to divergent, and adding a finite number to divergent will not convert it to convergent. So that means that if it's convenient when you're looking at a series and trying to see if it converges, you can actually skip the first finite number of terms that you want. You can say, well, let me just consider what happens after the 1,000th term or after the billionth term, because that's what's going to determine whether it diverges or converges in the end, is what happens as you go to infinity, not what happens for the first finite number of terms. So 3 is a more interesting, I think, point to think about. So let's look at an example of this theorem. So this is example 5 on page 637. So it says, let's see here, evaluate the following series. So this is the series as k goes from 1 to infinity of 5 times 2/3 to the k minus 2 to the k minus 1 divided by 7k. Doesn't that look fun? Okay, so basically the idea is we can see different pieces in here, and there's this constant multiple of 5 here, and we can just pull that out, and there's sort of 2 terms separated by the subtraction, and so we can distribute the series notation across that subtraction so that we don't have to deal with all of those separately, etc. So whatever the result of this series is, we can instead consider 5 times the series as k goes from 1 to infinity of 2/3 to the k minus the series as k goes from 1 to infinity of 2 to the k minus 1 over 7 to the k. So what I did is I just used two of the properties that we just wrote up of convergent series. One is that I can distribute across the sum or addition of terms of a series, and then two, that I can pull the constant outside. So that gets me to this point. So then if I'm trying to figure out how to evaluate this, I can observe that this part here is a geometric series with the number you multiply each time being 2/3. And so when you're multiplying by 2/3 every time, that's a number less than 1. That's going to cause the terms to shrink to 0. And we have a formula for evaluating a geometric series like that. Now over here, my concern is that I have the powers don't seem to match here. I have a k minus 1 up here, and I have a k to the 7th. I'm a 7 to the k down here. And so it's kind of hard for me to look at this as an example of just what's happening with the single power of k, because these seem to be mismatched every time. So here we would probably want to make like an algebraic adjustment or something like that. So I could, for example, take this and multiply this by 2/2, because that's multiplying by 1. So it's not going to change, the value of my expression. And so this 2 in the top is going to cause 2 to the first times 2 to the k minus 1 when combined to just be 2 to the k. And then the 2 on the bottom, I can pull out of the whole thing because of the property of pulling out constants. So this allows me to rewrite this as 1/2 and then have 2 to the k over 7 to the k times the summation. And if it's written this way, then we can see that this is 2/7 to the k, which is another example of a geometric series. So let's pause there and see if there are any questions about how I decomposed this series and worked with it to try to get to a point where I could try to evaluate it. Questions, comments, discussion so far?
Can you clarify why you multiplied by 2/2?
Yeah, so I wanted to try to somehow write this in a way where I could, because basically this is going up by a 2 every time on the top and a 7 every time on the bottom. But if the powers don't match, it's hard to sort of view it as something of this format, in which I could then say, hey, that's just a geometric series, and I can use the formula. So by getting the power on the top to be a k just like the power on the bottom instead of lagging behind by 1, that allowed me to basically take that common power of k and pull it outside of the whole fraction and recognize that I'm just multiplying by 2/7 every time. And I didn't need to do this algebraic manipulation to do that, as long as I recognized that. I could have just said, what is the first term of this geometric series, and recognize that it's a geometric series because we're multiplying by 2 on the top and 7 on the bottom every time, which means that that's a geometric series. You're multiplying by 2/7. But I'm trying to make it more obvious by doing this manipulation so that we can literally see this rewritten this way and recognize that that's a geometric series. Does that help, or is that more confusing?
That helps. My follow-up question, what happened to the -1? Because it's 2k minus 1.
Right. So if you multiply 2 to the k minus 1 times 2, which is why I did all this, you get 2 to the k minus 1 plus 1.
Oh, I see. Okay. Thank
And that definitely needs to be understood, because that's what motivated me to multiply by the 2 over 2 in the first place.
That's clear now. Thank you.
Yeah. Thanks for the question. Other questions or comments at this point for those who are following along and willing to ask? Okay, so let's try to start evaluating then. We're about 80% done with this problem. So what is my A value, meaning the first term in my geometric series in this first case? Well, when k is a 1, it's 2/3. So now over here, I have a geometric series. Where A and R can be determined. R is 2/7, multiplying by 2/7 every time. And when I plug in a 1, I also get 2/7 for my first term. So then what do I get? Now I have 5 times, and the formula is A over 1 minus R. So that's 2/3 over 1 minus 2/3 minus, and I can't forget this 1/2 that I pulled out, 1/2 times the result of this geometric series, which is 2/7 over 1 minus 2/7. Okay, so this would be 5 times 2/3, and it would be divided by 1/3, which is the same as multiplied by 3 over 1. And then over here, I would have 2/7, and it would be divided by 5/7. So that's the same as times 7/5. And these cancel. So this gives me 5 times 2 minus 1/2 times 2/5, which is 10 minus, and again, those cancel, 1/5. So that's, I'll just say 9 4/5. So this is using this property, the properties of convergence sequence or series, in order to sort of rework it and get it into a format where you can focus on the parts that you can evaluate. In this case, these two geometric series. Questions, comments about any part of that? Okay, so this is where 8.4 finishes. So any questions at all about any of the tests that we talked about? We introduced these 3 tests up here. We looked at examples of each, the divergence test, the integral test, and the P-series test. And then we added on at the end a theorem that helped us see some properties of convergence series. And that finishes 8.4.